Recall that the standard form of a linear equation is ax plus by equals c. When both linear equations of a system are in standard form, the system can be solved using a method called elimination. The elimination strategy adds or subtracts the equations in the systems to eliminate a variable. That's where it gets its name. So let's see an example of this. It says solve the following system by elimination. So when I look at this system, 5x plus y equals 44 and negative 4x minus y equals negative 34, I'm trying to look for those opposites or same coefficients. So here in the equation above, the y variables have opposite coefficients. You have a positive one and a negative one. So choosing which variable to eliminate, that variable y would be the easiest to eliminate because all we have to do is add the two equations together and it will go to 0. It cancels out, leaving us with x equals 10. Elimination, in one step, you've solved for one of your variables. We can then take that value of 10, and now it's very similar to substitution. We're going to substitute it into either equation. We're choosing 5x plus y equals 44 and putting the x in for the 10 in for x. And solve for y. If we simplify, we get y equals negative 6. So the solution is 10, negative 6. Plugging in x for 10 and y for negative 6 into both equations checks out as well, making that substitution and simplifying. So elimination brought us to our solution. It's another way, especially because we had opposite coefficients. We could just add the equations. Now let's look at another example. It says solve this following system by elimination. So again, 3x plus y equals 15 and negative 3x minus 3y equals negative 21. I'm looking for opposite coefficients or the same. So here in the above equations, the x terms have opposite coefficients, 3 and negative 3. They'll be the easiest to eliminate. When we add the two equations together, they go away. Then 1 minus 3 gives us negative 2y, and 15 plus negative 21 is negative 6, making our answer y equals 3. Now we can take the y equals 3 and make that substitution into either equation. They're choosing 3x plus y equals 15 and substituting in. If we solve, we subtract 3, divide by 3, you get x equals 4. So the solution to the system is 4, 3. It checks out when we substitute in x equals 4 and y equals 3 into both equations. 15 equals 15, negative 21 equals negative 21. So it checks out as our solution.
Step 1. Choose which variable to eliminate. Here, y has equal coefficients with the same sign, so y can be easily eliminated. Step 2. Either subtract the two equations or multiply one of them by negative 1 and then add them together. By either method, we find that x equals 3. Step 3. Then we substitute x equals 3 into either equation, and we solve for y. We get y equals 2. Then we check that 3, 2 is the solution by substituting those values into each equation and determining if the result is a true statement. Since they are both true statements, that is our solution.
Common coefficient. Sometimes it is not possible to eliminate a variable by simply adding or subtracting the equations. When this is the case, you need to multiply one or both equations by a non-zero number in order to create a common coefficient before adding or subtracting the equations. It's an extra step of work. Here's an example where this would apply. So it wants us to solve the system using elimination. But as the system is, I don't have the same or opposite coefficients. I have a 3x and 5x and a 4y and negative 2y. It's not easy to see which variable will eliminate. The y would be the easiest variable to eliminate though, because 4 is a common coefficient. Multiplying the entire second equation by 2 will make the coefficients become opposite. So if we take the second equation, 5x minus 2y equals 18, and multiply by 2, that will give us 10x minus 4y equals 36. So now together, we have our opposite coefficients, now 4y and negative 4y. So we can add them together to eliminate and get 13x equals 26 and x equals 2. So now, when x equals 2, let's substitute that into one of our equations here to solve for y. So 3 times 2 is 6. Subtracting 6 will get us negative 16, and dividing by 4 will make y equal negative 4. So together, 2, negative 4 is the solution. And if we have x equals 2 and y equals negative 4, giving our check, it works and makes both equations in the system true. In the previous example, the y was eliminated by finding a common coefficient of 4. Creating a common coefficient of 4 required one additional step, multiplying that second equation by 2. So either variable can be eliminated when solving a system of equations as long as a common coefficient is utilized. And that's just all about looking at the two equations and trying to find and create that. You have to make the decision yourself. Here's a different one. Now we have, or a different way, we have the same exact system, but now let's try eliminating the x. So we have 3x and 5x. So let's multiply the first equation by 5 and the second equation by 3 so that the coefficients will be the same. So the first equation we're going to multiply by 5 and the second by 3. Notice those numbers are coming from the opposite coefficients. We're multiplying the first by 5 since the other coefficient is 5, and we're multiplying the second by 3 since the first coefficient was 3. Distributing both will create new equations that now have opposite coefficients, 15x and 15x, so we can subtract, which will eliminate the 15x's, and 20y minus a negative 6y, 26y. Negative 50 minus 54, negative 104. And dividing by 26, we'll get y equals negative 4. We can now substitute that into either equation. So we're choosing this one, 3x plus 4y equals negative 10. Multiplying, changing to negative 16, adding the 16, and dividing by 3 gives us x equals 2. So we get, again, to negative 4 as our solution, and it works as our check as it did before in both equations. So whether you eliminate the y's or the x's, it's up to you. You have to make that decision. So each system here, you have to start to solve using elimination by asking which variable would you eliminate. And since none of these systems automatically have opposite coefficients or even the same coefficient, you have to ask yourself, what would you need to multiply each equation by? Again, there's no right or wrong answer as long as you end up with those opposite or same coefficients. So for the first system, I notice that there is a coefficient of 2x and 1x, and there's a common coefficient of 2. If I multiply the second equation by negative 2, I'll create my opposite of 2x and negative 2x. So in one step, I now can add my two equations together for my elimination. In the second equation, I have 3x and 5x, 8y and negative 6y. Now what I notice here in this system is that the y variables would be best to eliminate because I have a positive coefficient and a negative coefficient. So I need to still multiply both equations. Think 8 and 6 both have a common coefficient of 24. So I can multiply the top equation by 3 and the bottom equation by 4, and that will give me if I multiply through, it will give me 24y. And it will give me, if I multiply through the bottom equation, negative 24y, which will then eliminate. So there I was looking more at the fact that they had opposite signs. Very similar for the third system. I see my opposite signs, and I know that 3 goes into 6, that they have the common coefficient of 6. So I can multiply the bottom equation by just 2, and that will create, the top one will stay 6y, and the bottom will change when I multiply through to negative 6y. So you could have eliminated either variables. It's just going to, again, be what you see when you're solving the problem and what is going to be easiest or fastest to use that elimination method. Here's an example of solving a system using elimination where a special case arises. So we have 9x minus 5y equals 4 and negative 18x plus 10y equals 10. So we're solving using substitution. So the first thing we need to do is eliminate the y variables because we have negative 5y and 10y, and 10 is a common coefficient. So we're going to multiply the first equation by 2 so that the coefficients are opposite. Looking, negative 5 can turn into negative 10 very easily by multiplying by 2. So if we distribute the 2, that would create 18x minus 10y equals 8. Now the coefficients are opposites, so we're going to solve by adding the equations. So we will have the first equation times the first equation plus the second equation, which eliminates the y's. But in the same respect, it also eliminated the x's. Both variables eliminates. What we're left with is 0 equals 18. Is this a true statement? Well, no, 0 doesn't equal 18. That is a false statement. So there is no solution. Just like in substitution when you got a false statement, that meant no solution. So now here, when both variables eliminate, you'll end up with a false statement, which means no solution to the system. Here is another example of solving a system with elimination. That's a special case. Now we have negative 4x minus 10y equals negative 22, and 2x plus 5y equals 11. So we're going to multiply the x term in the second equation, because looking at the x's, it would be easiest to eliminate because 2 can easily multiply into a 4. 4 is a common coefficient. So we'll multiply the second equation by 2. We'll distribute through. That creates 4x minus 10y equals negative 22. The first equation, that then creates 4x plus 10y equals 22. And then we can eliminate the x's and the y's, and we end up with 0 equals 0. Is this a true statement? Well, yes, 0 equals 0. That is a true statement. So our answer from substitution, remember, was infinite solutions, infinitely many. So when both of your variables eliminate, you can either have a false statement for no solution or a true statement for infinitely many solutions.